Download this code from codegive.com, link in the description below. 28C3, The Science of Insecurity, a deep dive. The 28th Chaos Communication Congress, 28C3, held in 2011, featured a talk titled The Science of Insecurity by Thomas ptacek, Matasano Security, now NCC Group. This presentation explored the theoretical underpinnings of information security, moving beyond simple checklists and focusing on fundamental principles and how they are often violated in real-world systems. It emphasizes that understanding the underlying why behind security vulnerabilities is crucial for building more robust and resilient software. This tutorial will delve into the key concepts presented in the talk, providing explanations, examples, and code snippets, primarily in Python for clarity and simplicity, to illustrate the core ideas. We'll cover 1. Defining security and formalization * moving beyond vague notions of secure to define specific security properties and using formal methods to reason about them. 2. Abstraction and composition * how poorly designed abstractions and incorrect compositions can lead to security flaws. 3. Authorization models and access control * examining different authorization models, ACLs, capability-based, and common pitfalls in their implementation. 4. State management and time of check to time of use, TOC, race conditions * understanding how incorrect state management and race conditions can be exploited. 5. Cryptography as a tool, not a silver bullet * properly using cryptographic primitives to achieve specific security goals and recognizing the limitations of cryptography. 6. The human factor * acknowledging that humans are often the weakest link in security systems. 1. Defining security and formalization. The talk argues that security isn't a binary secure or insecure label. Instead, it's about defining specific, measurable properties that a system must maintain. These properties should be expressible in a way that allows us to reason about them formally. Example instead of saying this system is secure, we should say this system guarantees that no unauthorized user can access sensitive data, even if they have physical access to the server for up to 10 minutes. Formalization we can represent a security property as a predicate that must hold true for all possible system states and transitions. For instance, a simple integrity property. Why formalization matters * formalization allows us to use tools like model checking, static analysis, and theorem proving to verify that a system satisfies its security properties. It also forces us to think clearly about what we're trying to achieve. 2. Abstraction and composition. Abstractions are fundamental in software engineering. However, leaky abstractions and improper composition of components can introduce vulnerabilities. Leaky abstractions * An abstraction is leaky when its implementation details bleed through to the user, requiring the user to understand those details to use the abstraction correctly. Security often requires carefully controlling information flow, and leaky abstractions undermine this control. Example, path traversal via URL decoding * a web application might try to prevent path traversal by filtering out sequences in user-supplied file paths. However, if the application first URL decodes the input then filters, an attacker can bypass the filter using encoded representations like %2e %2e/. Composition * combining seemingly secure components doesn't guarantee a secure system. Interactions between components can create unexpected vulnerabilities. Example, cross-site scripting, XSS, and sanitization order * suppose you have two components, a template engine and a JavaScript sanitizer. If the template engine escapes characters after the JavaScript sanitizer has done its job, the escaping might introduce new characters that the sanitizer hasn't considered, leading to XSS. 3. Authorization models and access control. Authorization determines who can access what. Common models include access control lists, ACLS associate permissions with resources. User A has read access to file X. Capabilities associate permissions with tokens, capabilities. If you have the capability, you have the right. Role-based access control, RBAC assign users to roles, and roles to permissions. A simplified ACL system with indirection. Common pitfalls confused deputy problem a trusted component is tricked into performing actions on behalf of an unauthorized actor. This often happens when a component doesn't properly verify the identity of the actor requesting the action. Inadequate privilege separation giving a component more privileges than it needs. This increases the attack surface. Global mutable state authorization decisions based on global state that can be modified by anyone. Example, simplified confused deputy Explanation trusted component write _to_ file assumes the caller has already performed authorization checks. Bob, the attacker, exploits this trust by directly calling the function with a resource belonging to Alice. This is a classic confused deputy scenario. The trusted component is deputized by Bob to act on his behalf, even though he doesn't have the proper permission. Recommendation implement a robust and well-defined authorization mechanism. Use capabilities or ACLS with explicit checks at every point where access is granted. Practice the principle of least privilege. 4. State management and time of check to time of use, TOC, race conditions. State management security relies heavily on maintaining a consistent and accurate state. Inconsistent state leads to vulnerabilities. TOC race conditions occur when a program checks a condition, example file permissions, and then acts on it, but the state changes between the check and the action. An attacker can exploit this time window. Example, file deletion race condition Explanation the check _and _delete function first checks if file _path exists using os.path.exists. If it exists, it attempts to delete it using os.remove. An attacker, in the attacker thread, exploits the small window of time between the check and the delete. After the existence check but before the delete, the attacker changes the file permissions to make the file world writable, 00777. Now, even if the deletion fails due to permissions errors, because the file was initially read-only for the current user, the attacker has achieved their goal of making the file writable. This allows them to modify the file's content after the attempted deletion. Mitigation use atomic operations whenever possible. On Unix-like systems, use os.rename, or os.replace, Python 3.3+, to perform atomic file operations. These functions replace/rename a file only if the user has the necessary permissions at the time of the operation. Implement proper locking mechanisms if atomic operations are not feasible. 5. Cryptography as a tool, not a silver bullet. Cryptography is essential for security, but it's often misused. Encryption equals security. Encrypting data doesn't automatically make a system secure. You need to consider key management. How are keys generated, stored, and distributed? Compromised keys render the encryption useless. Authentication. Who are you encrypting/decrypting data for? If you encrypt data for an attacker, you're just helping them. Integrity has the data been tampered with? Encryption alone doesn't guarantee integrity. Use message authentication codes, MACs, or digital signatures. Side channel attacks attacks that exploit information leaked during the cryptographic process, example timing attacks, power analysis. Algorithm selection using outdated or weak cryptographic algorithms, example MD5, SHA-1, older versions of TLS. Example, insufficient integrity protection Explanation in the first, vulnerable example, we simply encrypt data using FIRNet. While FIRNet does include a MAC, relying only on FIRNet and not properly validating integrity yourself is risky. If the FIRNet library has a vulnerability, even in key derivation, it can lead to issues. An attacker could potentially modify the ciphertext. The second example shows best practice. We generate an HMAC, hash-based message authentication code, using the encryption key and the ciphertext. Then when decrypting, we first verify the HMAC. If the HMAC is invalid, we reject the ciphertext without even attempting decryption. This ensures that we are only decrypting data that has not been tampered with. Hamac.compare_digest is used for constant time comparison to prevent timing attacks. Recommendation understand the underlying principles of cryptography. Don't invent your own algorithms. Use well-vetted and established cryptographic libraries. Always verify integrity before decrypting. Handle keys securely. 6. The human factor. Security is as strong as its weakest link, and humans are often that link. Social engineering tricking users into divulging sensitive information or performing actions that compromise security. Phishing sending fraudulent emails that appear to be from legitimate sources. Password reuse using the same password across multiple accounts. Unpatched systems failing to apply security updates. Insider threats malicious or negligent employees. Example, phishing simulation, conceptual. Mitigation security awareness training educate users about common threats and how to avoid them. Strong passwords enforce strong password policies, length, complexity, multi-factor authentication. Patch management implement a robust patch management process to keep systems up to date. Access control limit user access to only the resources they need. Incident response plan have a plan in place to respond to security incidents. Monitor and audit continuously monitor systems for suspicious activity. Conclusion The science of insecurity emphasizes the importance of a rigorous, principled approach to security. It's not enough to simply follow checklists. You need to understand the underlying reasons why certain security measures are necessary. By formalizing security properties, designing secure abstractions, implementing robust authorization mechanisms, managing state carefully, and understanding the limitations of cryptography, you can build more resilient systems. And, critically, remember that security is a people problem as much as a technical one. Address the human factor through education, training, and careful design. By understanding these fundamental concepts, you can move beyond a superficial understanding of security and start building truly secure systems. Remember to always keep learning and staying informed about the latest threats and vulnerabilities.